All right, well, welcome back to Dynamics today, and we're going to be going through another type of coordinate system. This one's going to be cylindrical components, which is kind of interesting. I'm not sure if I'm sharing the right screen here. We're going to be doing, yeah, that's the one. Cylindrical components is another way that it's not quite like the NT system, but it's similar in that our axis is going to be defined by the particle rather than by some superimposed XYZ coordinate system, right? And so it's going to be most useful for when something has a circular or you know, somewhat circular pathway, especially when it is being impelled or compelled to move in some sort of pathway. That's when this one is especially useful. Something like a pathway like this, right? Where it's got something compelling it to move along that path, namely the normal force from the outside leg of this little, track that it's sliding in, right? That's going to be pushing it inward and making it curve. And so we could find out what that force is, for example. Um, Here's another example of that, right? The outside wall of the slide, keeping the kid from sliding out. She's also got a normal force underneath her, which, pushes up if she's sitting down on it. So we could find those different acceleration components, the one of up and down, obviously, with in the gravitational direction, and then the one making her go around the circle, as well as her tangential acceleration. Although in this one, our axes are not going to line up in the tangent and normal directions. They're going to be slightly different. So her velocity is actually going to have components in both directions. So we'll talk about that. Here is what that's going to look like, right? So we're going to have some point that is rotating, right? You could think of it as like a center of curvature, but the pathway might be different than that. We're not fitting a circle to it this time. So I shouldn't refer to this as the center of curvature. This is the center of whatever is rotating, right? Maybe this is an arm or some sort of mechanical device that's actually pushing the ball forward, right? And so it's got some sort of motor or some sort of mechanized piece that is rotating this radial arm, and that makes the ball move forward or the particle move forward, but it's not necessarily going to stay in that radius if there's a pathway also compelling it to move in a certain direction, right? So whatever spinning thing we have, we're going to start from its origin, right? From its center of rotation, and we'll draw a radial line through the particle, and that's going to be our R axis, right? Our radial axis. And then normal to that or perpendicular to that will be our theta axis or the transverse axis, which is just the direction that the arm is making it spin, right? So this is spinning counterclockwise. So our positive theta will point in the direction that agrees with that. So the R from the center here through the particle, perpendicular to that in the direction of the motion is our theta. So that's our new orthogonal axes. We've got the R theta system. So you'll notice the particle, it's going to be moving along this path. So its velocity is not 100% in the theta like it was with the NT system where velocity was 100% in the t, right? But this will be really useful, especially if we want to come up with, say, the normal force that this bar, that's in the R direction, right? How much force is that pushing the ball forward with, or the particle? And so that would be the acceleration in the theta direction, right? We could use to find that. We could also find what's the force that the track of the pathway puts on it, something like that. So the instantaneous velocity, we're still going to be doing dr dt, where r is the position vector. And as that changes per time, we're going to end up with two components now, because our velocity is not 100% in the theta or the r. right? We'll have a dr dt, r dot for the r component, but we'll have this r d dt of the in the r direction as well. If we use the chain rule for that to work these ones out, we'll simplify that to just this, right? We'll end up with in the r direction, r dot still, but in the theta direction, unit vector theta, we've got theta dot, right? And again, this is similar to last time, the book's way of making this a Cartesian coordinate vector, but instead of having I hat and j hat, we've got the unit vector r and the unit vector theta, right? We don't have a letter for those vectors, so we just give it a new unit vector defined by r and theta. So we can do it as a vector, but most of the time we're just going to be interested in that magnitude. So the amount of velocity in the r direction is the time derivative of r, and then r times the time derivative of theta is the magnitude of the velocity in the theta direction, right? And so we could get that. This is the theta component of velocity. This is the r component of velocity. We could square them, add them together, take the square root, right? Just a Pythagorean theorem. That is the total magnitude of the velocity. So we'll summarize all this here in a minute, but let's look at acceleration now. So if we do the time derivative of that velocity vector, now there's our velocity vector. We're doing the time derivative there. After doing that, we'd have some chain rules and some other things. We'll end up with some r double dots even. So on the r component, we'll end up with this when we take the derivative, and this for the theta component. So it's a little bit of derivation there, nothing crazy, but this is what we'd want to remember, is that those are the two components of acceleration in the r direction and in the theta direction. Excuse me. So there's the two components. We could add them together with Pythagorean theorem and come up with the magnitude of acceleration as well. And so in general, there it is. That's what we would want to note, is that in the r direction, we've got this for velocity, that for acceleration. In the theta direction, we've got this guy for velocity and this for acceleration. Now we also have the possibility for acceleration in the z, or a changing velocity, a changing position. But those ones are going to be pretty simple. It's just going to be the time derivative of whatever that z function happens to be. So we could have a z dot and then a z double dot for velocity and acceleration there. So putting it all together, got the components. We've written this several different ways, but if you don't write anything else down, these would be the ones to get on your note card for, what formulas you want to take into the test with you, for example. You've got the components of velocity in the two axes, and you've got the components of acceleration in the two axes. That's really what we'll use for this class. And then we could get the magnitudes of those by typical means, right? By what we've always done with the Pythagorean theorem. And that is the introduction of everything that we'll need for this fun. And so we'll try it out in an example here coming up.